And here we will talk about application of conditional expectation. So you will really see that it is application domain of this concept conditional expectation is so broad that it is solving various problems. So it is all about that. If you understand this one very good, then definitely most of probabilistic model you can easily solve. So my suggestion would be that just focus on the ultimate goal of what we call it conditional expectation. Also related concept that one is conditional variance as well. So if you understand about conditional expectation, then conditional variance would be not a not tough job to understand. You can easily understand that conditional variance as well. That would be also uh, a, a random variable or function of random variables and hence random variable like conditional expectation. So coming to outline of today's lecture, here I will talk about two kind of application. One application directly that will be followed from law of expectation. That means here you know that here it would be simpler kind of problem it would be, and later I will talk about uh, we will express probability as a conditional expectation. So itself you can see that it is really interesting kind of concept, and this concept is solving various problems. So I have taken various problem, lottery problem and other kind of winning of a lottery problem, and there are various other problem I will discuss here. And here when I talk about application of law of expectation, then one law of expectation I had already discussed about uh, iterated law of expectation. That means expectation of conditional expectation of conditional expectation equal to expectation of the uh, variable x, random variable x. So if you are having conditional expectation x given y, then you are finding we know that this would be a random variable, and if you find the expectation of that random variable, then that one is giving conditional expectation, and another name of this one we are calling it law of iterated expectation. So what is happening that it is very useful in sense in the problem that if you are having a random variable for which very difficult to find the expectation directly, so you have to come with some observation y, another random variable y. So it would be totally suitable kind of suitable pick from your side, that from the problem will suggest that what kind of random variable second random variable y you want to introduce in order to simplify the calculation of expectation of x. So it is just your user choice. Also you can say that user pick, user choice. Based on that you can easily in place of directly calculating this expectation of x, you can calculate this expectation very easy, and various problem will be depend upon that how we can do that. So such kind of application I will talk. And here when we are coming to here probability as a conditional expectation. So what just we will define a random experiment. From there we will take any event, uh, suppose we call it a, and that event, probability of that event we will try to express as a conditional expectation. That means conditional expectation of some, again another random variable y will come, expectation of uh, a given y. So this situation we will try to express. So this is the when you express the probability of a into in this form, then this one is really magical. Here magic is coming from y, that one is totally understood from the problem. From problem you can come up with a suitable y random variable, and through that you can do what conditioning over a, and with respect to that you can define conditional expectation of a given y. That would be again a random variable. If it is a random variable you can find the expectation, and if you are finding the expectation it would be equal to the probability of a. So that is the scenario we will discuss in detail. And what is happening that this approach is really solving many problems that you will see it here. So coming to first application of law of expectation, also I have included variance, although I haven't covered that conditional variance. Variance I have already covered. So in short I will cover the conditional variance a little bit here. After that I will mostly talk about the conditional expectation because that one is the major part of this lecture. So coming to law of expectation and law of variance, that means we are talking about result related to conditional expectation and conditional variance. That is the meaning. So we had already seen in the law of expectation, that means if you're trying to find expectation of x, and it is a little bit difficult job, tricky job. Why? Because of absence of a distribution of x. That means we don't know the productive mass function of x. Then if you don't know the productive mass function of x, how you can calculate the expectation of x? It is very difficult to calculate. And definitely you can able to calculate productive mass function of x from the problem, but that journey would be very difficult. So what you do, you will choose one alternative path. So in place of that, you will try to find in the problem itself one another random variable, which on which if you condition, then you will see that you will get a conditional expectation, and for computation of that expectation of that conditional expectation would be relatively easier. And we know, we had already seen that this expectation of conditional expectation is equal to expectation of x. So that's why in place of this, we will calculate this one. We will calculate this. So here in another way also we can call it this expectation of conditional expectation, we can call it average of case by case averages. The case by several cases, several scenario we are introducing in that problem, several cases or several scenario, that or rule, what we used to say, or summation rule or some rule, that case by case scenario that initially I had discussed. Through that you can find the expectation of x. So if you try to know further intuitive meaning of that law of expectation, that means law of iterated expectation, then intuition behind this formula is that in order to calculate expectation of x, one can break the sample space of x with respect to y, and then can take weighted average of the expectation of this conditional expectation, and where the probability mass function would come from the observed random variable y. That means y is very easy kind of random variable. That's why y is a very suitable pick. That means definitely you will have information about y, complete information about y. So by exposing the information of y, you can get expectation of x. That is the idea. Now, as we discuss here, conditional expectation with the same token, that means in the same framework, we can define for each observed value a conditional variance. How we define? We are defining conditional variance like variance of x given y, and we know that what is the definition of variance. So forget about your conditioning approach. Simply we will say like this way: variance is what? Expectation of a square of mean deviation. So here we are not dealing with directly the random variable x. We are dealing with another random variable, condition random variable x given y. X given y. So what is happening, that if you try to find variance of this one, so here condition we have to put here condition by y, and mean deviation, how we do? X minus what mean we will take, that conditional mean or conditional expectation we are taking here. In place of mean we are taking conditional expectation. So that is the definition of conditional variance for each y. And likewise, if you vary for every y, then we will get this will lead to a random variable, that would be what? Variance of, that means simply we can say that conditional variance, variance of x given y, that we are, in short, we are calling it conditional variance. And again it would be what? It would be again function of y. Case wise we are calculating, for each y we are calculating this conditional variance. That's why this conditional variance would be a function of y, and hence we can say that it is a random variable. So if it is a random variable, then it would have a variance, and it would have a expectation, variance, everything it would have. So one interesting relation with respect to variance of that undermine what random variable we are taking x. If you try to calculate variance of this one, expectation, we have already seen that in order to calculate expectation of x, we can apply this rule, that iterated expectation, the expectation of conditional expectation. Now another job is coming here. Through this conditional variance, we can calculate variance of x indirectly that would be also simple job to calculate. Here why we are calculating variance of x indirectly? Because we don't know the protein mass function of x. At first hand we don't know. So that's why there is a issue. So that's why we are. It is very difficult to calculate variance of x. So indirectly, how we can calculate? We can calculate it through conditioning approach. That we introduce conditioning by some observe suitable peak of random variable that we are calling it y. So this variance of x, it can be bifurcated into expectation of conditional variance plus variance of conditional expectation. So if you want to see the derivation is very simple. I am giving this one as a homework. You can try it. And what is the hint? Hint is that if you try to derive any kind of result in mathematics, what is the technique? That technique always proceed with the concept which is containing most of information. So it is a homework. Try to drive this result. It is very easy. You want to find. So among these three terms, variance of x, expectation of conditional variance, variance of expectation, conditional expectation. Now anyone tell me which among these three, which one is containing most number of information? Anyone would like to comment over it? You are having three terms. One term is variance of x, another term is expectation of conditional variance, third one is variance of what we call it conditional expectation. Then tell me which one is containing most number of information. Anyone? Are you able to understand my question or not? Okay, yes, one. Would you like to answer it? Variance of what? Just you can use microphone. There is no issue because those are mathematical terms, very difficult to write in that simple in chatting box. So anyone, which would be easier, and which would be more beneficial to proceed with? Here simply, if you proceed with the variance of conditional expectation, this one is containing most of the information. So start with this one and keep on proceeding. Keep on proceeding. Whatever that definition of variance of conditional expectation is saying, keep on doing, and while calculating at the end, you will get that this result, complete result you will get. So that is the. So your starting a step would be that start with this one, and finally you will get this final result. That is the. So I have given it. So based on that, try to find this result or establish this equality. So further, like conditional expectation, here we have already seen that the conditional variance, it is a function of y, while variance of x given y, that is conditional variance, it would be a random variable. And if you ask the randomness in that conditional variance, where does it come? It is coming from randomness of y, not because of randomness of x. It is coming from randomness of y. Why? Because in the definition you might have already seen that x will be adjusted, it will be finished. You will see that x completely it will be adjusted due to that nature of expectation. Only y would be there. So that's where randomness of conditional expectation or conditional variance is sources from uh, randomness of second variable y, on which we are putting conditions. So that is the source of randomness. Now, I will talk about one simple example here. We will take conditional expectation as a random variable, and if it is a random variable, then we will find variance, we will find expectation, we will find probability mass function, everything we will find. So here we are taking a question like this way. So a simple one thing I had already mentioned, that conditional expectation is a random variable with randomness inherited from the randomness of y, not from x, because x will be adjusted here. X will be adjusted, so that's why we are not randomness is not coming from x, it is coming from y. Now here one question is that we are having a random variable y, which is taking two value. So that means it is Bernoulli in nature. Y is taking value 1 with probability 1 by 8, and y is taking value 2 with probability 7 by 8. So that is the situation. Okay. Now we are defining a conditioning over x, another random variable x, for which we don't know the probability mass function. Just we are having information that we can, by conditioning on x, we can get uh, distribution of that conditional distribution of x given y, conditional probability mass function of x. That means we don't know probability mass function of x pxy, it is unknown to us, but we know about px given y. We don't know this, but we know that what is conditional probability x given y. This we know. What is that? That one is given that x given y, this x given y is defined as twice of y with probability 3 by 4 and thrice of y with probability 1 by 4. So question is coming here, we have to find the conditional expectation of conditional expectation. We have to find the conditional expectation, and what is the probability mass. If it is a definitely it is a random variable, then what is the probability mass function of that, and further related parameter, that expectation and variance also we will calculate. Okay, so here we will go case wise. If you are taking y equal to 1, then what would be conditional random variable x given y equal to 1? It would be what it will take value 2 with probability 3 by 4, and it will take value 3 with probability 1 by 4, and hence we can find conditional expectation of x given y equal to 1 just using the definition of this from here. What it is talking about, directly from here you can borrow the conditional probability mass function for x given y equal to 1. Y equal to 1 easily you can given, you can get it x given y equal to 1. You can get it. What is that? It is taking value 3 by 4, probability 3 by 4 when this y equal to, when x given y it is taking value 2, and when x equal to simply 2, and it is taking this conditional probability mass function is taking value 1 by 4 when x is taking value 3. So this is the conditional probability mass function for x given y when you are taking y equal to 1. Likewise, so here you are having the value of x, also you are having the probability mass function of x given y for y equal to 1. So you can easily calculate this conditional probability. That one is what, 9 by 4. For y equal to 2 also you can calculate the corresponding conditional expectation. That one is 18 by 4, and hence we can say that so we are having all possible value of conditional expectation. It is taking two value, again binary situation. So binary situation is borrowed from the binary nature of the suitable random variable x given random variable x, y given random variable y. It has been borrowed from there. It is not because of x, because it is because of y. So the conditional expectation is taking 9 by 4 with probability 1 by 8 and 18 by 4 with probability 7 by 8. So from here we can say that what is the probability mass function of conditional expectation. We are giving a name to conditional expectation z. It is a random variable, so we are giving a new name z. So what is the conditional expectation of z? So we can say that it is taking probability 1 by 8 when z is equal to 9 by 4, and it is taking probability 7 by 8 when z equal to 18 by 4. So this is the probability mass function of conditional expectation. So all these are borrowed from y. You can say that all these are borrowed from y, and this is the probability mass function of z. And from here you can calculate, if you want to calculate expectation of z, easily you can calculate, because you are having probability mass function, you are having value of those observed values. So easily you can calculate whatever parameter you want to calculate. You can easily calculate those things. So it is a binary situation, easily very simple to calculate. Calculation is very simple. Now we will go to talk about another interesting problem, that this one is related with mouse in a maze. So suppose there is a mouse in a maze, and there would be several do to exist to come out from that maze. Then we have to find the expected time that the mouse will take to come out from that maze. So this one is really interesting kind of problem, and it can be solved with the help of law of expectation. So problem is coming like this way. Am I audible or not? Anyone respond? Am I audible?
Yes, sir.
Okay, fine. So here we are going to discuss about the problem mouse in a maze. So a mouse is a trap in a room with three exits at the center of a maze. So exit one is talking about that leads to outside the maze after 3 minutes. That means after 3 minutes, if that mouse is taking path one, then that mouse will come out of the maze uh, after 3 minutes. Then there is a second path, second exit that leads back to the room after 5 minutes. So if that mouse opt for second path, then that second path it is not going outside the maze. It will make uh, trapped again in the room. So after 5 minutes, that mouse will come back to the room again. Now there is one more path. That path is saying that path 3 is saying that again that path will lead that mouse back to the room after 7 minutes. So most interesting kind of path is path 1. So that will always uh, go out, but situation is that mouse is not having idea which path that that mouse will choose. That mouse is, and all these three paths are equally likely. Assumption we are taking that all these three paths are equally likely for the mouse. So mouse can take any of these three with equal probability 1 by 3. Okay, then question is coming here. What is the expected time taken for the mouse to leave the maze? So here situation is coming like this way. This is the room, and if mouse is opting for path 1, exist 1 or path 1 with probability 1 by 3, within 3 minutes mouse will come out of the room. But if mouse is taking path 2, then within 5 minutes, after 5 minutes, mouse will come back to the room. There is no outgoing. Okay, and for similarly for uh, path 3, mouse will know mouse will not able to go out of the room. So these 2 and 3 are complicated kind of things, and each path selection is having probability 1 by 3. So that means if you define a random variable associated with that selection of path, then easily it is uh, very much clear that we know the distribution property mass function, and we know the value that those every information is there. So that one is a candidate of y, but question is related with what is the expected time taken. So the random variable associated with time, that would be very difficult because we don't have distribution of that. Directly we don't have distribution. So anyone can answer right now? What would be the best that expected time taken for the mouse to leave the maze? Okay, let us simplify this. I will go to define random variable. First, we are defining x random variable. That one is the complicated one, that desired one. Okay, x is talking about time taken for mouse to leave maze, starting from room R. This room R, I can give a notation R. Okay, and y are defining the exit or the path the mouse chooses. It might be 1, it might be 2, it might be 3. So value of y would be what? Simply it may be path 1, it may be path 2, it may be path 3. And what is the distribution of y? What is the probability mass function of y? Anyone? I told that it is equally likely situation is there. Selection of path is equally likely. So that's why probability mass function for this y is 1 by 3. That means y is completely known to us. It is a very suitable kind of peak. Now, but question is coming with, we have to find expectation of x. We don't have much information about x. We have partial information about by y. We are able to observe y. So we have to find expectation of x. So here we will apply law of expectation. So what we will do, we will find expectation of x indirectly as a expectation of conditional expectation of x. expectation of conditional expectation of x, because the conditional expectation, it happens to be function of what we call it y, and when you find expectation of function of y, then you can apply expected value rule, and there that would proceed with what distribution of y, and distribution or probability mass function of y is already known to us, so we can easily proceed with that. So that's why here we are further writing expectation of x. How? Because this conditional expectation would be at what discrete random variable, so just summation, and summation y is taking three value running from 1 to 3. Here this one is the function of y, this conditional expectation would be function of y into probability mass function of y. That information is directly coming from expected rule that we know. And here the function, this probability mass function of y, it is what? It is a fixed function 1 by 3, constant function 1 by 3. So 1 by 3, it will come out of the this summation, we can come it out. So that's why I have taken it out, and just I'm writing each term for all three value of y. So this one is with respect to y equal to 1, this one is with respect to y equal to 2, this one is with respect to y equal to 3. So our job is here to find this expectation of x given y equal to 1, expectation of x given y equal to 2, expectation of x given y equal to 3. If we are able to compute this from this information, then our job is done. That will give the overall expectation of x. So how we can calculate? What is the value of this one? First one, expectation of x given y equal to 1. So what kind of situation it is taking? What kind of situation it is talking about? It is saying that mouse has observed that path 1. If mouse has observed path 1, so what would be expected time? The expectation of x given y equal to 1. What would be this? Anyone? Yeah, 3 minutes, because path 1 is taking 3 minutes to come out of the room. So that's the value of this one is 3. And tell me what would be about this. If I'm talking mouse observed that that mouse have to take path 2. Mouse observed path 2 and trying to proceed with that. In that case, what would be expectation of x given y equal to 2? What would be this? Y equal to 2 is talking about 5 minutes, not 5 minutes. So expectation here, x is a random variable, that one is talking about time taken for mouse to leave the maze, so it would be 5 plus something. What would be that something? Any idea? This not 3, because here this y equal to 2 is totally different from y equal to 1. Here just here you are observing y equal to 1, you are not observing y equal to here actually you are observing y equal to 2, you are not observing y equal to 1. It is different case wise. I told that case wise, this one is the first case, this one is the second case. So we are trying to find expectation by case wise approach, case wise average. So it is different, so definitely it is mutually exhaustive with respect to this. So we will not talk about that we simply forget about. Just here y equal to 2 is talking about we are having only information about second gate, second path. So what would be 5 plus what it would be? 5 plus, yeah, nice, 5 plus EFX, because after this taking second path, he will come back to room. So again that mouse will have the same situation, he could not come out from that room, so same situation. So that's why expectation of x. Likewise in the 3 it would be what? Similar logic you can give, like 2 it would be 7 plus expectation of. Now you got representation of these individual expectation like this way in term of expectation of x. So can you find what would be the expectation of x? So put all this value and simplify it, and that simplification will lead to that expectation of x would be 15. This we are calling it worst case scenario. 15. Best scenario is 3 minutes. Worst case scenario is 15 minutes. Definitely, if mouse is choosing for second one and could not come out from the room, definitely next time mouse is not going to choose that path. Mouse will choose another path to come out of the room. So that is the very simple. Definitely mouse is having memory. It is not like that memorylessness. So that is the, so that's why this expectation is coming. It is the 15 worst case scenario that we are calling it. The best scenario is 3. So this is the solution that we got it from iterated law of iterated expectation. So definitely here there was no need to calculate probability mass function of x. By using the probability mass function of y, we can calculate expectation of x. So that is the approach. Now I will talk about one more problem. That one is dealing with swimming with dolphins. Yes. Yeah, definitely. Not problem. Mouse is having memory. It is not like that mouse is having some geometric kind of a random variable nature. Geometric is memory. That random variable is geometry having memorylessness property. I am not giving that assumption. By default, you should consider that. Okay. So I will go further. I will talk about swimming with dolphins. So this problem is like this way. Fraser runs a dolphin watch business. Okay, so every day he is unable to run the trip due to bad weather with probability P. What is the probability of bad weather? That one is P, and it is independent of all other day. It is not like that it depends upon previous day. It is not like that. So that probability P, it is independent of other all other day. Okay, that is the situation. Now further, Fraser works every day except the bad weather days, which he takes as a holiday. Then what is question? Question is that we have to find the expectation and variance of the number of customer Fraser sees between any two bad weather day, any two bad weather day. So we have to find the expectation of and variance of number of customers that Fraser sees between bad weather days. So that we have to find it. So this is the problem. So this problem we can uh, solve it, tackle it with the help of conditional expectation. How? So we are defining suitable random variable first here. Y is talking about the number of consecutive days Fraser has to work between bad weathers, and X is the desired one that we want to find. X be the number of total customers who go on Fraser's trip in this period of Y. In this period of Y. So tell me what kind of distribution Y would have. Y is talking about number of consecutive days Fraser has to work between bad weather days. And X is the number of customers who go on Fraser's trip in this period of Y. So definitely X will have very complicated distribution, but Y would have very simple kind of distribution. Any thought? Okay, see it here. So we what in order to calculate the expectation of X, we have to condition on Y, and hence so the conditional random variable X given Y, it would be actually you can call it binomial random variable, but talking about number of customers who go on Fraser's trip in this period. So period word is mentioned here, and what is the best suitable random variable is coming in to model such kind of counting occurrence. That one is the Poisson random variable. When some period, some kind of time interval is mentioned, so better we always model that Poisson. You can go with binomial, there is no issue, but problem with binomial would be that that the probability of success would be very small and number of trial would be very big. And if you are going to calculate then p to the power n would come, m is p is very small and n is very big, then in that case what would have happens, that quantity computation would take time. So better approximation will be given by Poisson distribution. That's why we will model this problem with Poisson distribution. That's by condition on y, we model this number of customer by Poisson distribution. And y is talking about number of consecutive days. So if you talk about what would be the parameter of this one, it would be just multiple of those what we call it number of consecutive days between bad weather. Between bad weather, how many consecutive days we observe. So that's way, that is the parameter for this conditional distribution. Now further we consider that success be bad weather, because probability of bad weather is given p. So that's why we consider success be bad weather and failure be work day. So what is the probability of success? That is the probability of bad weather, and that one is given equal to p. So probability of failure, that means probability of work day would be 1 minus p we are having. Now here I have taken y as a simpler suitable p of random variable on which we will put condition. Then what is the distribution of y? It is taking very simple kind of distribution. What is that? It is talking about number of failures before first success. Number of failure so y is what number of days between two bad weather day. So that means good day, or what we call it work day, suddenly bad weather, that is the success. Bad weather is the bad weather day is the success. So fine day or sunny day also, you can say that sunny day, finally you rainy day, you got rainy day or bad weather day, that would be your success. So what is coming, it is just talking about geometric instance, geometric nature. Good, suddenly bad. So that situation is coming. That's way the distribution y of y, it would be geometric distribution. It will have a geometric. So the geometric distribution, so what is the probability mass function for geometric? Failure, then success. Failure, what is the probability of failure? 1 minus p. How many failure we observe? Suppose y is taking value k. In kth observation, there is a success. Then we will talk about for before that k trial, we have observed k minus 1 failure, and at the kth trial we observe success. So that's where distribution would be 1 minus p, 1 minus p to the power k minus 1 into p. This is the geometric probability mass function. So y is having a geometric probability mass function, very easy to find. And what is the mean of that? 1 minus p divided by p, easily you can find it out. That, and variance would be 1 minus p divided by p square. We had already discussed all this, mean and variance of geometric random variables, so you can calculate. So you are having every information of y. That's why very nice to proceed with y. We don't have much information about x, but we are having every information about y. And now only information we are having that by condition on y, x is a Poisson distribution with this parameter mu times y. So we have to find mean of this and variance of this. So very easy to find mean of this conditional. It is Poisson. So what is the mean of Poisson? It is coming equal to same parameter. So mean of this conditional random variable, it would be equal to mu time y, and variance would be also mu time y. So that those things also we had already discussed. So if you are taking a Poisson distribution, then mean and variance both are same. That one is equal to the parameter, the involved parameter of the distribution. So parameter of the distribution for this conditional random variable is mu into y. So that's why we are able to calculate. Now here, in order to calculate expectation of x, we will apply law of total expectation. So we are applying our, so how to calculate expectation of x. So in order to calculate that, we are calculating expectation of x, conditional expectation x given y. So we are calculating this one on what is the mean of this one, what is the expectation of x given y. That one is mu time y. So this expectation is equal to expectation of mu times y, and mu is what? It is a constant number. It is talking about how many times time. So times okay, and y was what number of good day between two bad weather day. So that's way mu will come out, and only we will have y, and y is what? It is geometric random variable. That means we know the uh, probability mass function of y, and hence we know the expectation of y. That one is 1 minus p divided by p. So we got the expectation of x easily. Here we don't need to find the probability mass function of x. By using the probability mass function of y, we can calculate the expectation of x. Similarly, we can calculate variance by using law of variance. So how we can calculate? We can calculate like this way. So variance of x can be expressed as expectation of variance, conditional variance, plus variance of conditional expectation. Now we are having all these. We know about this. We know about this thanks to y. So expectation of conditional variance would be equal to expectation of mu times y, and variance of conditional expectation would be equal to variance of mu times y. So because both are same, so just calculate. Mu is constant, it will come out, and here expectation is a linear operator, so linearly mu will come out. But if you talk about variance, variance is not a linear operator, it is quadratic operator, you can say that. So quadratically mu will come out as a square term. Mu square is coming out. So mu square times variance of y. Variance of y is what? It is already here. 1 minus p divided by p square, and expectation of y is 1 minus p divided by p. So substitute all this value here, and you will get the variance of x as well. So this is the expectation, and this is the expectation, this is the variance. So you got it through law of expectation. So there was no need to calculate probability mass function of x. So that's why this rule is very interesting. I will talk about one more application. That one is talking about that probability we represent as a conditional expectation. So how we represent? Here we need to introduce indicator function. So everyone might be aware of indicator function. What is indicator function? Anyone know? So suppose you are having a set A, then over this set A you can always define a function. One function always you can define, indicator function or characterization function. There are various names. 2R, I'm calling it. It is defined like this way. That means it depends upon what here A may be anything, we don't know. A is just a set. It can be, it can contain any kind of object. Okay, so indicator function we are defined like this way. So indicator function is taking value 1 if, call it here argument omega. It is suppose taking argument omega. So if you are taking element from the set A, then that element will map to 1, and if you are taking element from outside the set, that will map to 0 under the indicator function. This is that means it just indicate the element of A only. It is not bothering about it. It is sending all those elements which are outside, sending to 0. That means nullification is happening. So that's way indicator function is really interesting kind of approach, and it is always irrespective of any event. Indicator function is always a Bernoulli random variable. So you can say that it is always defining a Bernoulli random variable. Okay, so using that concept we can introduce probability as a conditional expectation. How we will do it? So here consider an event that one is happening with probability A. That means we know the probability of that event. Then we are willing to express that as a conditional expectation. How we can express? So what would happen? The probability of A, and we know from the Bernoulli random variable. What is the beauty of Bernoulli random variable? If you try to find expectation of a Bernoulli random variable, then expectation of Bernoulli random variable would be equal to the probability of success. And here what indicator function IA, it is a Bernoulli random variable. So that's the expectation of this Bernoulli random variable, it would be equal to probability of success. That is talking about probability of A. happening of A, that would be success. So this probability of A is equal to expectation of the corresponding indicator function for the set A. Now here we will apply law of iterated expectation. That means we will express this one as expectation of conditional expectation IA given Y, and Y is your choice. You can come up with Y. It would be totally very simple kind of thing. That means we are having every information about Y is the partial information regarding that thing. So why we are having Y is the partial information. That means the means everything we know about Y. So we are applying conditional expectation, law of conditional expectation. Okay, or so we can further here indicator function is taking two value, either 0 or 1. So that's way if you try to find, so if you try to find it explicitly, then it would take this form. Rightly I'm writing it. So one case would be IA equal to 0 when elements or outcomes are not coming from A. Another case would be IA equal to 1 when outcomes are coming from A. That's where 0 times probability mass function of Y, that would be meaningless here. That will go to 0. So we are not considering that one, only we are considering the case with respect to IA equal to 1, in value of indicator function equal to 1. So that's why here this conditional expectation is equal to expectation of this probability. Again it is a function of Y, we are conditioning over Y. So we can say that I equal to 1, it is again, what does it talk about? It is talking about probability of A given Y, probability of A given Y. So just we have to find this way. So you can easily see that here this probability of A has been expressed as a conditional expectation, this conditional expectation. So in next class I will talk about really interesting kind of approach. What is that? One approach is that winning lottery game. It is already more than 45 minutes. So in next class I will discuss that problem, and also I will give one assignment based on this probability as a conditional expectation in next class.